Suppose you are playing with blocks and you are stacking them to form pillars. And you put several pillars side by side so that no pillar on the right is taller than a pillar to its left. In this case, we have something called a Ferris diagram or Young diagram. Now suppose that when placing the blocks one by one, you further impose a rule that at any juncture, no pillar on the right is taller than a pillar to its left. Then what you can do is you can write in the order number in which you place the cell. So for example, I place this cell first, this cell second, then this cell third, this cell fourth, this cell fifth, and so on. And what I described earlier in terms of the condition that at any juncture, no pillar on the right is taller than some pillar to its left, is equivalent to saying that the numbers which denote the cell placement order must form increasing sequences from left to right in each row, as well as increasing sequence in each column from bottom to up. Such a valid recording of the cell placement order is called a Young tableau. The natural question is, given a Ferris diagram with n cells, how many ways can I be placing my blocks one by one in a valid way? So in other words, how many valid Young tableaux are there? Now to answer this question, we are going to have to introduce some notations. So it's typical to denote a Ferris diagram by lambda and the height of the pillars by lambda 1 to lambda k, where k is the number of pillars. Now, the condition that no pillar on the right is taller than a pillar to its left is given by this non-increasing property of the pillar heights. I'm also going to have to reference my individual cells, so I'll be using a XY coordinate system to refer to individual cells. So this cell over here, for example, is 3, 1. Now to tell you the number of valid Young tableau, I'm going to have to introduce the concept of a hook. So a hook essentially for a cell I, j is going to be all the cells at I, j and above it and to the right of it. So it's a L shape where the corner of the L is at the required cell I, j. Another example, the hook of this cell over here would be this L shape. I'm going to denote the hook length by little h. And the hook length refers to the number of cells in the hook. So in this case, the hook length of 3, 1 is 4 because there are 4 cells in this hook. So in this diagram, you can see the hook length of all the different cells being filled in. So for example, this cell has a hook length of 7 because its hook is this L shape over here. The surprising thing is that there is a formula relating the hook length and the number of valid Young tableaux. So the hook length formula tells us that the number of valid Young tableaux is given by n factorial divided by the product of all the hook lengths across all the cells. So in this case, for example, there are 13 cells. So the hook length formula tells us that the number of valid Young tableaux is 13 factorial divided by the product of all these hook lengths denoted over here. So this evaluates to 11,583. A very surprising formula. And the goal of this video is to prove the hook length formula using a very interesting combinatorics / probability proof. Now, there are many proofs out there and they are all quite complicated. For example, this paper that says a simple proof of hook length formula involves some crazy algebra like this and looking at things like residue from complex analysis. And mind you, this is just part of the paper. It is not the entire proof. So our combinatorics and probability proof is also going to be somewhat complicated, but I hope it is going to be very interesting, and at least we won't have to deal with crazy algebra like this. So without further ado, let us take a look at this proof that we'll be doing. So the name of the game here is the following. We have f lambda denoting the number of valid Young tableaux for a given Ferris diagram lambda. And we let E lambda be this quantity that you compute by just using the formula. So given lambda, you can go through and find all the hook lengths and compute this quantity. And the goal is to show that this quantity equals the number of valid Young tableaux. And the strategy here is we are going to be doing some form of induction. So we are going to write a recursion that expresses the f and e lambdas in terms of smaller Ferris diagram. So the key concept here is the concept of a corner cell. So we define a corner cell to be a cell that has hook length of 1, which means there's nothing above or to the right of it. So for example, these are the corner cells in this Ferris diagram. So there's two observations to be made. The first is that in any valid Young tableau, or equivalently any valid way of placing the cells, the last cell that you place must be a corner cell. The second observation is that deleting a corner cell gives you another valid Ferris diagram. So these two observations combined together tells us that we can write f lambda recursively in terms of the f's of smaller Ferris diagram, namely f lambda equals the sum of f mu, where mu equals to Ferris diagram we obtained by deleting a corner cell C. So the different mu's are basically a breakdown of the different cases where the last cell you place is either this corner cell, that corner cell, or the other corner cell. So hopefully this recursion formula is clear. So the general strategy, as I mentioned, is we are going to use some form of induction. So we are going to let you check that the base case is very simply equal, and we have this recursion for f. So we need to just similarly show that the same recursive relation hold for E. And once this is shown, then by induction, the f will be equals to E for all Ferris diagram lambda. Okay, to show this, we are equivalently going to just move the E lambda over and show this instead. So for a given lambda, you want to show that the sum of E mu over E lambda as mu varies equals to 1. And this should remind you about probability, because the sum of probabilities that cover the entire universe of possible outcomes must equal to 1. So indeed, what we are going to show is a probabilistic scenario where the E mu over E lambda reflects some form of probability. So consider the following game. This game starts off by letting you select any cell in the Ferris diagram uniformly at random. And then from your current cell, you go to any new cell in its hook, excluding itself. So basically pick from H, excluding the cell itself, uniformly at random. So for example, maybe you start off here, then you can go to any of these other 6 cells. So there's 7 cells in its hook, but you exclude itself in the next iteration. And you keep doing this until you reach a corner cell, because that will be the end where you cannot go to any new cell in its hook. So the claim that we want to prove is that for any particular corner cell C, the probability that you finish there out of all the corner cells is precisely E lambda take away C divided by E lambda. So where E is given by the numerical formula here. So if we can establish this claim, then the sum of probabilities over all possible outcomes, which is all possible corner cells as the ending, must equal to 1. So that would prove the whole hook length formula based on the recursion that we want. So in other words, we have reformulated, simplified the problem to the following. Show that for a particular corner cell alpha, beta, the probability that you finish there among all corner cells is given by this expression, where E is given by this formula. Let's simplify things a little bit, because this ratio have many terms that cancel out. So what we observe is that this ratio over here can actually be written by this formula. It looks a little bit confusing, so let me explain how this formula is obtained. So basically, you notice that if you take the ratio, firstly, the top will have n minus 1 factorial instead of n factorial, whereas for E lambda, this is n factorial. So the factorial part in the ratio becomes 1 over n. Now, secondly, we have product of all the hook lengths. Now, after removing this corner cell, most of the hook lengths are going to be unchanged. So for example, this cell, the hook length will still be 4 in the new Ferrous diagram and the old Ferrous diagram. What are the cells where hook lengths are affected? Basically, the cells that are affected are those in the same row or column as the corner cell being removed. So for example, this cell over here, the hook length used to be 5, but you remove this, so the hook length became 4. Another example, this cell over here, hook length used to be 3, but after removing this, the hook length is 2. So you notice that hook length in the same row or column as the corner cell is going to be decreased by 1. So which is why most of the products cancel, except for those cells which are in the same row. So beta is the height, right? It's the y coordinate, same height as the corner cell, but all the other cells from x coordinate 1 to alpha minus 1, their hook length decreased by 1. So they don't cancel the original hook length. So this is why you have this formula over here, and same for all the cells in the same column as the corner cell being removed. And this is just algebra where I write this fraction as 1 plus this fraction. Okay, so now I can reformulate my problem again to say that I want to show for a particular corner cell, the probability that you finish there when you play your game is given by this expression over here. Okay, now we can finally try and tackle this probability problem. A few observations to be made. First is that if you play the game, your path will only go upwards or rightwards at each step. And that is because when you have at a particular point, your next cell is going to be either it's going to be one of the cells in the hook accept itself. So it's either going to be upwards or to the right. So what we are going to do also is introduce notation for the cells that you stop at along the path. You can call them alpha 1 b1 to alpha 2 b2 until alpha k bk, where k is the number of steps you take in the path. And what we are going to do is, this is the most critical one, we are going to let A be the set of x coordinates that you hit, and B be the set of y coordinates that you hit. So just now you saw that your paths are over here. So your A is this x coordinate, this x coordinate, and this x coordinate, and your B is this y coordinate, this y coordinate, this y coordinate, and this y coordinate. So that is the definition of A and B. So for a given path, you can construct a A and a B. Now we are going to flip the situation around. So from here, I'm going to flip the situation around. Now instead, I am going to define P subscript AB comma P subscript AB bracket capital A capital B as the probability that your path produces capital A and capital B as the XY projection. given that you start at A, B. So now this, where I have A, B written as subscript here, I'm saying, suppose I start here and I play the game. I can obviously take a lot of different paths from here on. I might even end up here. I might end up here. You know, so for each path, you can have some A and some B. What is the path, the probability that the A and B you get is these two sets that you define here. Now we shall only consider sets with mean A equals A and mean B equals B, because otherwise the probability is obviously going to be 0. And for simplicity, we are going to fix the corner cell we are interested in, alpha, beta. So we shall only answer the question for A and B with max A equals alpha and max B equals beta. And this is the lemma that we would like to prove. This is the answer. What is P of capital A, capital B? It is given by this formula, which is quite ugly. So let me explain how you get to interpret this formula. So the product over here involves the hook length of all these intersections over here that are in the same, so you have a net over here with the A and the B's, and in the topmost row, these are going to be having the same y coordinate as beta, and your x coordinate is going to be elements of A that is not equals to alpha. So these are the intersection points that are not the corner cell. So this formula over here, this product, same thing, it involves hook lengths of all these cells over here. So in the last column, but excluding the corner cell itself. So alpha is the x coordinate of this one, the rightmost x coordinate, and your y coordinate is all the elements of B excluding beta itself. So we are going to be taking the product of 1 over hook length minus 1 as will vary across these 5 points over here. Okay, it's a bit complicated, but let's take a look at the proof of this lemma. So for the proof of this lemma, we are going to introduce some notation. So let's say the A and the B that you put in here is A1 less than A2 less than dot dot. So A1, A2 dot dot, B1, B2 dot dot. Obviously A and B, A1 is small a and B1 is small b. So in order for you to succeed and produce capital A and capital B as your projection sets, your path that starts here must, as the next step, go to either here or here. It must go to either A2, B1 or A1, B2. Because once you go past that, right, you cannot backtrack. You can only go upwards or rightwards. So obviously you go up, you cannot go up too much, you cannot go up too little. You must exactly be here so that the next produced B is here. Or if you go right, you can only go until exactly here. You cannot go too short because you will get a new A value which is wrong. And you cannot go past it because you cannot backtrack. So your path must break down into two scenarios, either go here or go here, which means that the probability of succeeding is the probability of going here and succeeding plus the probability of going here and succeeding. So the probability of going to the correct A2, B1 and succeeding, firstly is you choose A2, B1, which is 1 over the number of options in the hook, times the probability of being at A2, B1 and succeeding, which means that your projection set is A take away A1 and B. So same thing, the probability of going up to A1, B2 and succeeding is the probability of choosing the cell out of the hook options times the probability of being at A1, B2 and having projection sets A and B take away B1. So once you have this, again, a recursive type of formula, you can apply some form of induction. So if we assume that your smaller cases are all proven, then this expression here is the same as this product, except you have A1 missing from your set A. So this product over here will be repeated, except that you do not have a copy of A1 beta inside the product. So you have this formula is H A1 beta minus 1 times this product times this product. Same thing, this product over here is the same as this original product, except you do not have a copy of alpha B2 alpha B1 inside here, because your B takes away B1. So same thing, you have the original product, but you get rid of your copy of alpha B1. So plugging in the induction hypothesis, you basically have your original product, but in the numerator you have the A1 beta minus 1 plus alpha B1 minus 1. And this fraction over here is equal to 1 because the numerator is the same as denominator. And this is another interesting combinatorics observation. Hook length of A1 beta is basically this part. So the hook length here, this L shape, plus the hook length of this, which is this L shape, is the same as this hook length plus 1 extra, because this L shape and this L shape double counts this. And then you can transfer this length down here and this length down here, so you get the same hook length here, except the double counting here. So that's why with the extra minus 1, this numerator equals the denominator. So with this, we have proven that this formula is true. It's the product times the product. Phew. Okay, so now that we have proven the lemma, we are basically already almost done, because to find the probability that you finish at alpha, beta, you basically sum over all possible scenarios, which means you sum over all possible starting point. Then you have 1 over n, which is your probability that you started there as your starting point, times the probability of you succeeding when you start at a, b. And the probability of you succeeding when you start at a, b is the sum over all possible valid projection sets that you get. And by valid, it means that your smallest a is small a, and your smallest b is small b, and your max a is alpha, and your max b is beta. So by considering all valid projection sets and summing them, you get the probability of succeeding ending at alpha, beta when you start at little a, little b. And the double sum here, if you think about it, is equivalent to saying that you consider all ways of picking subsets from 1 to alpha, where you definitely pick alpha. So you definitely pick alpha, so now you care about all possible ways to pick subsets from 1 to alpha minus 1, and all possible ways to pick subsets from 1 to beta minus 1. So by summing over all possible subsets here, you get the double sum here. And then you plug in the formula for P proven by a lemma. So now what you realize is that if you look at your original thing that you want to prove, this product, if you expand out all the products, right, in each term you either pick the fraction or you pick 1. So basically your final sum over here after you expand is basically all possible combinations of picking or not picking, which means it covers all combinations of picking subsets from 1 to alpha minus 1 and all subsets from 1 to beta minus 1. So expanding this product gives you back exactly this formula over here. And so with that, this concludes the very long and complicated proof. So for those who managed to make it all the way to the end of the video, congratulations. I hope you enjoyed this video thoroughly. It is insanely cool combinatorics and probability proof. Stay tuned to the channel for more math videos, and I will see you in the next video.